Hello everyone. The title of this video is Graphing Exponential Functions. Alright, so in this video I'm going to be doing examples that are taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 6.2, called Graphs of Exponential Functions, and I'm under the heading Graphing Exponential Functions. Alright, and each example I do in this video will either be an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Alright, so under graphing exponential functions, we're going to be graphing the most basic version of an exponential function, or what they might be calling the parent exponential function. And then in the next video, we'll talk about transforming this function into a more complicated one, graphing using function transformations, which I'm assuming you remember from chapter 3 of this text, right? I've done videos on function transformations from chapter 3. So I'll read over this little box here with you, and then I'll just do a couple examples and be done. So the parent exponential function, the most basic, looks like this. Y equals, or f of x equals, b to the x power, right? Where b is called the base, right? And the variable, the input variable, the x, is in the exponent, right? Thus the name exponential function. We also have some conditions on the base, right? The base needs to be a positive number, and also the base can't be 1, right? Because that wouldn't be interesting either, right? And you saw in section 6.1, my section 6.1 videos, that there's a reason why the base is not negative and the base can't be 1, because those are cases that are, especially when the base is negative, some bad things can happen. So we need to have a positive base. Right? So this basic exponential function has the following characteristics. It's a one-to-one function, and again I'm assuming you remember what that means. The graph has a horizontal asymptote of the x-axis, or the line y equals 0, so on either the right end or the left end, but not both, the graph will approach the x-axis, not actually touch it though. The domain is all real numbers. The range is all positive numbers only. Right. No x-intercepts. As I mentioned, the graph is not touching this horizontal asymptote, not touching the x-axis. A y-intercept of 0, 1, right? B to the 0 power. Anything that's not 0 to the 0 power is 1. And it's an increasing function. It increases from left to right if the base is bigger than 1. Or they would say it's an exponential growth model, if it increases as you increase the input. And it's decreasing from left to right if b is less than 1. And if b is less than 1, they might also say that it's an exponential decay model or decay function, and they give you some pictures here. Right. If the base is bigger than 1 for just plain old b to the x, and if the base is between 0 and 1, if, again, you're just graphing this basic y equals b to the x power. Right. Okay, so I'm just going to go straight into I just have a couple examples, really just one of each, an exponential decay and an exponential growth example. And I'll show you some other things that happen, when you play around with the base in Desmos. So here, again, graphing exponential functions. First example, I'm asked to graph f of x equals, 0.25 to the x Or, if you want to write 0.25 as a fraction, it'd be 1/4 to the x, right? But you see it's got that form b to the x where the base is between 0 and 1. Right? So this is going to be an example of an exponential decay function. It's going to be decreasing from left to right when I graph it. Alright, so I'm going to simply, and then I'm asked to state the domain, range, and asymptote. Right? But it's going to be the same domain, range, and asymptote for any function that's just b to the x, a positive number to the x power. Now I could do it by hand. And remember, anything to the 0 power is 1. So you have 0, 1 on the graph, right? That was mentioned earlier in that box from the textbook. The y-intercept is 0, 1. Then when I plug in, 1, 1/4 to the first power is 1/4, right? So it gets smaller as I move to the right, and that's what I mentioned about it being a decreasing function. Then plug in 2 for x, and 1/4 squared is 1/16, right? It's a quarter smaller, so it's even tinier. And then 3 for x, you get 1/64. 4 for x, you get 1/256. But no matter what you do, no matter what you plug in, it's going to get smaller and smaller and smaller, but never actually be 0. It'll always have some positive value. Right, so that's why they say this has a horizontal asymptote, right, of the x-axis. The graph approaches this horizontal line, in this case, as you move to the right. As x goes to infinity, the function approaches y equals 0. All right. Now for negative powers, and again, I'm hoping you're familiar with some exponent properties. When you raise something to a negative power, it's just the reciprocal of the positive power. So 1/4, to the negative 1 would be the reciprocal of 1/4 to the 1. 1/4 to the 1 was 1/4. The reciprocal of that is 4. So input -1, output 4. And then, -2 would have an output of 16. And -3 would have an output of 64, right? So as I move to the left, the graph shoots up quite rapidly, forever. And it's something like this. And again, they call this exponential decay. Right, as you move left to right, if it's a decreasing function. Right, we have a decreasing function here. And once again, I'll write this out now. They might call this an exponential decay model or an exponential decay function. Decay for decrease as you increase x. And as with all those parent functions, those basic b to the x functions, the domain of an exponential function is all real numbers. Right, so you can plug in anything from negative infinity to positive infinity on the x-axis. The range, as with all the parent exponential functions, these basic b to the x functions, is only positive numbers. Right? Everything above 0 is an output, but not 0 itself, and nothing below 0 is an output. And I already mentioned the asymptote. Okay. Alright, and then let me go to the Desmos website, look at a little better picture. My hand drawings aren't the greatest. So remember, there's a free online graphing calculator at desmos.com. And I'm going to put in, say f of x equals b to the x power, and add this slider for b, and then just have the value of b be 1/4, 0.25. Right. And you see the picture that I have here. Right? And if we make a table, see when when x is 1, you get a quarter. When x is 2, this is 1/16, 0.0625. When x is 0, you get 1. When x is -1, you get 4, -2, 16. All the points that I plotted by hand. And you can see the asymptote, at the x-axis, right? It looks like it's touching it right now, but if you zoom in close enough, you'll eventually see that the graph doesn't actually touch the x-axis, right? It's always a little bit above it. Right? Always just a little bit above it. Okay? Great. All right, so my next example is just the other case, right? Just a couple cases here, one with exponential decay and the other with exponential growth. F of x equals 4 to the x. This time the base, right, that b to the x, the base is bigger than 1. So this will be, when we're eventually done graphing it, this will be an increasing function. If it's just, again, only if it's b to the x can you say this. If I had like something to the negative x or some other transformation going on here, things might change. But if it's just b to the x and b is bigger than 1, it's going to be an increasing function, right? As I move to the right, the graph will go up, the outputs will increase. And they'll call this, therefore an exponential growth model. And again, just making a hand drawing first. And again, you plug in 0, you get an output of 1. Right? 4 to the 0 power would be 1. And then 4 to the first power is 4. Right, so 1, 4. And 4 to the second power would be 16, right? And it would grow quite rapidly as I move to the right. And then as you move to the left, it is going to approach the x-axis, but not actually touch it again. Right? Again, the x-axis will be an asymptote. We saw 4 to the -1 is 1/4, right? The reciprocal of 4 to the 1. 4 to the -2 is 1/16, right? A quarter of that. And 4 to the -3 would be 1/64, and so on. But always positive. Right? Always has a positive value. And as I move from left to right, the output goes up sharply, is increasing. Right. So again, asymptote of the x-axis, y equals 0. Domain, as in all those parent exponential functions, all these exponential functions have the same domain of all real numbers. You can plug in whatever you want for x. It's the range, that's not all real numbers, right? The range for these parent functions, these b to the x functions, is positive numbers only. Right? Now, of course, the range will change when we perform transformations, right? If I move it up or down or flip it over the x-axis or something, right? If I perform transformations, this range may change. The domain won't. But this range may change when we perform transformations, and we'll see that in the next video. Pardon me. So yeah, back here, I'm just going to change b to 4, and you see now it's definitely a exponential growth function, increasing as I go from left to right. Again, it looks like it's touching the x-axis, but if you zoom in close enough, it's not. Right, it's approaching the x-axis on the left end. Domain's all real numbers, range is all positive numbers. It's got all the same points on it. And then again, I put the slider up here so we could just play around with this. See, anytime the base is bigger than 1, I shouldn't have negative bases. So let me change this up here. Let me just go from 0 to 10. And have it just go by 0.1s, go by tenths. Right, so you see when the base is bigger than 1, you definitely have an increasing function, right? 2.8, 2.6, right? Blah, blah, blah. Now, now the reason we don't have the base equal to 1 is because when the base is equal to 1, it's just a horizontal line. Right? You'd have y equals 1 to the x, y equals 1. That's a horizontal line. There's no exponential growth or decay there. So we don't consider that an exponential function. And then, as we saw with 0.25 and stuff earlier, when the base is less than 1, you see the exponential decay start to happen. It becomes a decreasing function. Right? Okay. All right. So I'm hoping that's good enough here for the parent functions, and that's all I'm doing in this video. So I'm hoping that watching me just do these couple examples helps you in some way, when you're asked to graph one of these basic parent exponential functions on your own. And thank you very much for watching.